Welcome to The Explainer. Today we're unpacking one of the most brilliant, absolutely essential concepts in computer science. If you've ever wondered how your favorite apps pull your exact data out of massive databases literally in the blink of an eye, well, you're in the right place. We are demystifying hash tables, the ultimate engine of instantaneous data retrieval. So grab your engineering hats, because we're going to look at this strictly through a programming lens. So picture this. You're standing in a library with millions of books, and you need exactly one specific title. If you start checking shelf by shelf, book by book, it's going to take you an eternity, right? In computing, checking one by one is a linear search, and for modern systems, that is just way too slow. The fundamental question for us as software engineers is, what if we could jump to the exact location of that book instantly? That huge leap from blindly searching to knowing exactly where to look, that's the entire magic of hashing. Here's our mental roadmap for today's explainer. First, the need for fast retrieval. Second, mapping data to memory. Third, step-by-step hash functions. Fourth, handling memory collisions. And finally, real-world applications. Let's jump right in. Starting off with Section 1, the need for fast retrieval. Okay, let's break down this bottleneck. In standard searching, without hashing, your search time scales with a number of items. You have n items, it takes big O of n time. If your database doubles in size, your search slows down right along with it. But with hashing, our search time drops to big O of 1. That means retrieval is practically constant, whether you have 100 records or 100 million. For any CS student out there, you know that achieving O of 1 is basically the holy grail of efficiency. Moving to Section 2, mapping data to memory. To really get hashing, you just need two basic concepts. First up is the hash table. This is simply an array used to store records. Think of it as those giant empty bookcases in our digital library. Inside that array, we have buckets. A bucket is just the specific individual slot on the shelf where your actual data record is going to live. But here's the million-dollar question. How do we know exactly which bucket to drop our data into? Enter the hash function. It's just a mathematical formula that takes a piece of data, we call that your key, and converts it into a specific index in our array. The output of that calculation is your hash address. So your key goes in and out pops the exact memory address. It's essentially an automated catalog system letting us completely bypass the need to search. All right, Section 3, step-by-step hash functions. Let's pop the hood and look at the math. We'll start with the division method. It's beautifully simple. Step 1, take your key. Let's say it's the number 47. Step 2, apply a modulo operation using the size of your table. Say our array holds 10 items, so 47 modulo 10 gives us a remainder of 7. Step 3, store your record exactly at index 7. Boom! It's fast, it's deterministic, and it maps any number directly into our fixed memory slots perfectly. But division isn't the only game in town. Check out the mid-square method. Step 1, you literally square the key. So 25 squared is 625. Step 2, extract the middle digit. In 625, that's 2. Step 3, store the data at location 2. Now, you might be wondering, why do this? Well, squaring the key wildly scrambles the digits, and grabbing the middle gives us a beautifully pseudo-random, uniform distribution. It helps spread records evenly across the entire hash table. Okay, but what if your key is massive? That is where the folding method shines. Say your key is 1, 2, 3, 4, 5, 6. You can't just crunch that without causing some serious system overhead. So step 1, split the key into chunks, like 1, 2, 3, and 4, 5, 6. Step 2, add those parts together, which gives us 579. Step 3, apply the modulo to that smaller sum to get your hash address, giving us a 9. It's an incredibly clever trick to break down massive keys into manageable bytes, completely preventing system overload. Moving on to Section 4, handling memory collisions. What happens when we hit a traffic jam? So here's the narrative plot twist. We're trying to map a virtually infinite number of possible keys into a finite amount of memory. Eventually, inevitably, two different keys are going to produce the exact same hash address. It's like two librarians trying to shove completely different books into the exact same spot on the shelf. We call this a collision. Say key 15 and key 25 both hash to index 5. They can't both fit. When a bucket gets completely full, you get an overflow. Now, as programmers, we can't just let the program crash. We've got to resolve it. The first way to fix this falls under open addressing, and the simplest form is linear probing. If bucket 5 is full, well, you just find the next empty slot sequentially. You check bucket 6, then 7 until you hit an open space. Super easy to code, but there's a catch. You have to watch out for primary clustering. Data starts clumping together in these big, ugly sequential blocks, and that severely slows down your future searches. So, to avoid that nasty clustering, we can step up to smarter workarounds, like quadratic probing. Instead of checking the very next slot, it jumps using squares, checking slot 1, then slot 4, then slot 9. This spaces the records out really nicely. Another brilliant move is rehashing, sometimes called double hashing. If you hit a collision, you just run the key through a completely different secondary hash function to grab a brand new address. It takes a bit more computation, sure, but it gives you excellent data distribution. But what if we just don't want to steal empty slots from other records? That brings us to chaining. Separate chaining is incredibly popular. If bucket 5 is full, you don't hunt for an empty array slot. Instead, you just attach a linked list right onto bucket 5. It allows for basically unlimited growth. Alternatively, there's coalesce chaining, which links buckets internally within the table itself using pointers. It's a highly efficient use of memory for more advanced implementations. Looking at these methods side by side illustrates a core truth of computer science. Literally everything is a trade-off. Linear probing, simple to write, but you get clustering. Rehashing gives you the absolute best distribution, but it eats up more computation time. Separate chaining is amazingly flexible, but demands extra memory for all those linked list pointers. Choosing the exact right compromise for your specific build, that is what separates good coders from great engineers. And finally, Section 5, Real-World Applications. Let's look at where hashing actually lives. Guys, these aren't just dry academic concepts. When a massive database instantly retrieves your user profile, that's database indexing powered by hashing. When you log into your bank's website, password verification systems use hash functions to safely check your credentials. Compilers use symbol tables to instantly retrieve variable names. Caching systems, search engines, network routers, and literally the entire foundation of blockchain cryptography, they all rely 100% on the instantaneous O1 retrieval techniques we just walked through. Which brings us to our final thought. Hash tables are absolutely the speed demons of data structures, turning the seemingly impossible task of searching millions of records into a virtually instantaneous operation. You now understand exactly how data maps to memory, the step-by-step math behind hash functions, and the clever ways software engineers resolve memory collisions. So, knowing that hashing powers the absolute fastest systems on planet Earth, how are you going to implement it to optimize your next software build? Thanks so much for hanging out with me for this explainer. Keep coding, and I'll catch you next time.